All right, hey everyone. So I'm Tristan Noth, and today I'm going to talk to you about resource-guided program synthesis. So synthesis considers the problem of generating executable code from some sort of high-level declarative specification. And synthesis technology has come a long way recently. We can generate recursive programs in high-level languages and even provide formal guarantees that the generated code actually satisfies our specification. For example, let's imagine synthesizing a function that returns the intersection of two sorted lists. Type-directed synthesis lets us specify functions like these with rich type signatures. And then there are synthesizers that can regenerate a recursive implementation from this type, like the code shown here. But let's take a closer look at the actual code we got from the synthesizer. Common does what we asked it to do. It'll return the intersection of two lists. But even though it works correctly from a functional perspective, it runs slowly. The problem is that Common iterates through one of the input lists, and then it calls this member function on every iteration, which then searches the entire second list for a matching element. And then since member might have to traverse the entire list, this runs in quadratic time. But the thing is, a clever programmer might notice that there actually is a linear time implementation. This version here runs in linear time by traversing both lists simultaneously, inferring whether or not a given element might be in the intersection from the sortedness of the inputs. If the head of one list is smaller than the head of the other, we know that we can safely drop it from the intersection and continue. And this is a general problem. Right now, synthesizers can't reason about resource usage, so they can't tell the difference between these two implementations. They tend to just return the first program they find that satisfies the functional specification, whether or not it might happen to be efficient. And we need a synthesizer that can reason about resource consumption. We want to be able to extend functional specifications with some directions to optimize for some notion of resource consumption, and then have the synthesizer return an appropriately efficient implementation. This work is going to address this problem. I'll tell you about the design and implementation of Resin, the first resource-aware synthesizer for functional code. So there are three main challenges in developing a resource-aware synthesizer like this. The first is specification. Prior work tells us how to use a type signature to specify the functional properties of this function, but we want to extend this spec with information about resource consumption. Then we have to figure out how to actually generate code. In general, synthesis is a two-phase process. There's a search algorithm that enumerates candidate programs, and then a verifier that attempts to rule out invalid possibilities. So I'll tell you about how we use the information from the specs to automatically verify resource consumption. And then I'll tell you about what this looks like in the context of search and how we use it to prune the search space. So first, let's talk about specification. So let's go back to this same intersection example. There are two parts to this specification. For the functional part of the spec, we can use refinement types. But then we need a way to specify information about resource consumption. So we're going to put a bound on execution cost by annotating the refinement types with this information about resource usage. So the type-directed approach like this lets us build upon previous work from this community in both type-directed synthesis and in type-based resource analysis. The sync-with synthesizer can generate code from refinement type signatures, but we're going to use it as a general framework for type-directed synthesis. Then to integrate resource analysis into this process, we're going to adapt a technique called automatic amortized resource analysis to this context. So before we get into the resource analysis, let's talk about how we specify functions with refinement types. So a refinement type is just a simple type annotated with a logical refinement. For example, the natural numbers are those integers where the value is non-negative. And we can use types like this to specify the common function. We know that common is going to take in two sorted lists as input. So we've defined this slist type elsewhere, which is just the type of sorted lists. And then common is going to return a list, but we want to make sure that the elements in this output list are in the intersection of the two input lists. So sync-with will generate code from a type signature like this. We also need to give it a set of components. It's basically going to be enumerating candidate programs, and we need to give it a set of library functions so that it actually can build programs. But once we've done that, sync-with will generate the slow recursive implementation I showed you earlier. So now let's talk about how we're going to extend these kinds of specifications with information about resource consumption. We're simply, for now, going to add an annotation to each refinement type, which we'll call potential. And it basically means that the amount of potential a type has is the amount of resources available in a value of this type. And we can use these resources to pay for some operation that has non-zero cost. So where the refinements for Boolean expressions, these potentials are now numeric quantities of some resource. So let's see what it looks like on our example again. You'll probably notice that I haven't actually talked about any specific resources at all yet. And for now, we're just going to count recursive calls. But in general, the type system does support custom user-defined cost models. But for now, a simple model should be enough to guide the synthesizer to a more efficient version. So we want to give the synthesizer an upper bound on resource usage. So we're just going to annotate the type variables in the lists with 1 unit of potential, meaning that both lists, every element in both lists can be used to pay for a recursive call to common. And just like Sync-Would, we also need to give Resin a set of components. And in particular, we want to tell the synthesizer that member is going to traverse the entire input list. And that means we're going to, again, annotate these type variables with a single unit of potential, which means that member might have to make 1 recursive call per element in the input list. So now, hopefully, this will be enough information to guide our synthesizer towards the fast implementation. The specification now is 2 parts. We've got a functional part, and we have a resource bound, as well as, of course, our set of components. And given these, Resin finds the fast implementation that we hope it would. So now you've seen what the specifications look like. So let's talk about how we use this information to automatically analyze resource usage. So let's go back to this slow version of common. How do we know that it's going to exceed the linear resource bound we want? Basically, the problem is the sequential application of member and then common. We don't have enough units of potential at the top level to pay for both function applications, since both member and common require the input lists to carry potential. So we need to figure out a way to automate this kind of reasoning. And what we're going to do is reduce this problem to solving a system of linear arithmetic constraints. And these constraints are basically going to correspond to attempting to partition the resources we are given between the different function applications. So if we look at the specification again, you'll see that at the top level we're given a list with 1 unit of potential on every element. The question now becomes, can we partition these resources between all the function calls we might have to make? In particular, we need to make sure that this resource bound holds for any execution path through this program. So we're going to look at the application of member in the guard of the conditional and then the call to common in the first branch for now. So to figure out if we have enough resources, first we're going to annotate the program with these symbolic resource annotations. We don't know yet if we can partition the resources, so we're going to reason symbolically to allow a constraint solver to do the work. So first, let's look at the member application. Again, the second argument needs to have potential on every list element. And as always, type checking a function application requires checking that the list is a subtype of the formal argument. But the novel part here is how we're going to define subtyping. So subtyping between 2 lists reduces to subtyping between their elements, as usual. But then we need to check that a resource annotated type is a subtype of another, which requires not only checking subtyping between the base types, but also that we have at least as much potential as is required. So if we go back to the example, the subtyping check is going to induce a numerical constraint on our symbolic resource annotation P. And again, we're asserting that these list elements have to have 1 unit of potential. So if we look at the common application now, essentially the same thing is going to happen. We're going to get a subtyping constraint and then the corresponding numerical constraint. So like I said, we know that we want this bound to hold for any execution path. So we need to be able to share the top level resources between all the function applications on some path through the program. And that's what this notation here means. The sharing relation asserts that we can partition the resources from the top level of the program between the function calls on the path, which in this case is member followed by common. And just like subtyping, we're going to get a numerical constraint, which in this case is just an arithmetic partition. We need to make sure that the resources from this path through the conditional expression add up to the amount of resources we were given at the beginning. So now if we look at the entire system of constraints, including those subtyping constraints that we generated earlier, you'll see that this is not satisfiable. We can't partition one unit of resources into two values that need to both be at least 1. So to automate this, we'll send the constraints to an SMT solver, which of course confirms that it's unsatisfiable. So now I've shown you how to automatically verify resource usage. Let's look at what it looks like in the context of search. So one naive way to approach this problem might have been to modify any general purpose synthesizer to generate a stream of functionally correct programs until one of them satisfies the resource bound. This would be easy because we could use any synthesizer and any whole program resource analysis, but it's inefficient. We want our analysis to actually guide the search and prune the search space. And the technical challenge here is that existing resource analyses are whole program, whereas we want the type system to be able to locally analyze incomplete candidate programs and prune the search space in that way. So I'll show you how this works now. Incomplete programs like this are going to arise as we enumerate candidate programs. And if we can reject something like this, we're pruning away a lot of our search space. And it turns out that the analysis I showed you earlier works in this case. It's the right thing to do. We don't need to know what goes on in the else branch to know that this is going to exceed our resource bound. And it's never going to meet the specification. So when we reject an incomplete program like this, we're actually rejecting every prefix or every suffix of this program and rejecting an entire family of programs. And therefore pruning much more effectively than we could have with a whole program resource analysis. So in fact, it's worth noting that we don't even need the function applications to be complete. In this case, as soon as we apply comment to y's, we know that this program is prefix is never going to satisfy our specification. So I've shown you a little bit about how Resin works. Now I'll show you what it can do. So we focused the evaluation on 3 questions. Can Resin generate faster programs than Synquid can? How much longer does it take Resin to generate programs? And then finally, does this local resource analysis actually guide the synthesizer? So let's start from the beginning and look at the actual code that Resin generates. So first we ran Resin on all the Synquid benchmarks, and we can generate all of those with a linear resource bound, but out of these we can only find faster implementations on 2 of the benchmarks. But it turns out this isn't that surprising. The benchmarks are generally carefully curated, so they have the exact set of components needed to quickly find an optimal implementation, and most of them are impossible to optimize. So to better answer this question, we added another 13 benchmarks, and out of these we can find a faster implementation of 9 of them. For example, this function removes adjacent duplicates in a list, and Synquid finds an exponential time version by making an unnecessary recursive call. Here, we're inserting an element into a sorted list, and we don't change the asymptotic complexity, but we can avoid unnecessary recursive calls by using dependent resource bounds, which tell the synthesizer to stop recursing as soon as it's inserted the element, essentially. So now let's compare the performance. In the median case, Resin is about 2.5 times slower than Synquid. If we look at the benchmarks that are significantly slower, many of them are those on which we actually find a faster implementation, which again is somewhat unsurprising since we're always going to be exploring more programs in this case. Some of these other cases are those where we use a dependent resource bound, which requires a more expensive constraint solving algorithm that you can read about in the paper. So let's consider the final question. Does this local analysis actually guide the synthesizer? Another way to ask this question is what happens if the analysis is non-local and we can only analyze complete programs? So to answer this, we implemented the enumerate and check approach I mentioned earlier. And here, it performs similarly, except in a couple cases where it blows up and times out after 10 minutes. And these are the cases like common, where the structure of the program changes significantly, which I think indicates that this local analysis is going to become more important as functional specifications get more expressive and we can generate more complex programs. So today, I've shown you how we brought resource analysis into the domain of program synthesis and how we built a synthesizer that generates not only recursive functions, but proofs of their functional correctness and that they satisfy a given resource bound. So thanks for listening. I think there's a lot of interesting work to come in this direction. Examples and code are all in line.
Hi, my name's Rishi from University of Texas. So I was wondering, would these annotations require that the user knows beforehand what resource usage they're looking for? And is there any way to infer what the resource usage could be?
Yeah, so for now we're using concrete annotations, but the automated amortized resource analysis does support inference. And I think moving forwards, like with more expressive bounds, it'll be very restrictive to rely on concrete annotations like this. But for now, we are explicitly specifying these properties.
Great, thanks.
Okay, let's thank our speaker again.